In Chapter 14 of Graphs and Digraphs, we study vertex colorings. One of the most fundamental parameters involving vertex colorings is the chromatic number of a graph. And so we introduce vertex colorings through this in the first section. Now, graph colorings, it has been said, it's one of the most popular subjects in graph theory. There are tons of papers and a huge body of knowledge done on graph colorings. So in this video, we are going to introduce some preliminary concepts, terms, and definitions. We'll look at a couple examples of graph colorings, and we'll build to this first parameter of graph colorings, the chromatic number of a graph. Let's get started. So what we mean by a vertex coloring is just an assignment of colors to the vertices of the graph. So you can think of this like you're coloring the vertices of the graph. But without any restrictions, there's not a whole lot to study here. So what we study are vertex colorings in which adjacent vertices are colored differently. We call these proper vertex colorings. Since this is primarily going to be our topic of study, we'll usually just we'll refer to these proper colorings as just colorings of the graph. So instead of actually coloring the vertices of the graph, and so the notation and the analysis is a little bit easier, we just use the integers 1 through k as our colors. So we can think of this sort of like we're labeling the vertices of the graph with this set of labels. These are our colors that we get to use. And so really what we're studying here is a function from the vertex set to the natural numbers, right? That assigns each vertex a color, which we're representing with an integer, or rather a natural number. And this function has the property that the color of u is not the same as the color of v whenever the two vertices are adjacent. And so this is really what a graph coloring is a function with this property. Right, so if we use, usually we use the smallest ones, but however many colors we use for a given coloring, so whatever number k colors we use, we call this a k coloring of the graph. And so we're typically looking at functions like this. All right, so let's actually take a look at an example here. Here I have the same graph twice, and we're going to investigate this in each case. So we'll give two colorings here, is what I mean. So let's see. Let's just look at a proper, let's say we want to produce a proper vertex coloring of this graph. All right, so I'm going to assign colors to each vertex. I can think of this like labeling. And let's see, let's just try and come up with an example of a proper vertex coloring. So let's say V1 I color 1. And then V2, which is adjacent to it, I would need to color 2. V3, it's adjacent to this V2, so I could color it 1, or I could color it some new color. Let's call it 3. I'm going to call it 3. And since I just want to get a proper vertex coloring, I'm not going to limit myself to too few of colors. So maybe I'll label V4 4, and I'll label V5 5. Why not? And let's see. Let's try and color the rest of this now that I've decided these colors. So U1 up here is adjacent to a vertex colored 1 and a vertex colored 2. So one thing I just can't help but do, all of the information is given by the actual number that I'm writing next to the vertex. But for those that can see colors, I'm going to add some color to this. I'm going to use white for my 5th color here, because it can just be very pretty if you're able to see all of the colors. And V2 and U1, so U1, right, it's adjacent to a vertex colored 1 and a vertex colored 2, and so I would have to use this vertex 3. I could use 4, or I could use 5 here and still have a proper vertex coloring. So how about I label it, how about I color it 3? Let's see, U2 here is adjacent to a vertex colored 2 and a vertex colored 3. So I could label this one 1. All right, I could label it 1, 4, or 5. So I'm just going to do 1. I'm going to use 1. And now this U3 here, it's adjacent to a 4, a 3, and a 1. I could do it 2. I could color it 2, though. I'll color it 2. Let's U4, 5, 4, and a 2. So I'm going to color that red. How about it? And then over here, this is adjacent to a red, a white, a red, and a green. Sorry, a 1. Keep forgetting the colors. A 1, a 5, a 1, and a 3. And so maybe I color it 2. And so what we've done here is we've given a proper 5 coloring of the graph. Right, and just to illustrate this notation, so the color on vertex, right, the color on vertex, let's say U1, is 3, right, and the color on U2 is 1, etc. Just to see this as a function. And so the question is, can we do any better? Because clearly if I'm using less colors, that's more restrictive, and it might not even be possible for me to give a proper K coloring for a given value of K for this graph. Perhaps I can't even do a proper 4 coloring. I don't know. Let's try and do a proper 4 coloring of this. Well, notice here I only used color 4 once in this, and let's see. It's adjacent to, unfortunately in this one, it's adjacent to a 1, a 2, a 3, and a 5. And so it looked like there I really did need this 5th color, which I call, which is color 4 here. But maybe there's a way I can do this that eliminates that color. So for example, notice that I can swap color 2 and color 5 here. If I if I swap color 2 with color 5 for these 2 vertices, so 1, can I do that? Yes, if I do that, this will be colored 5, and it's adjacent to a 1, a 3, and another 1, and so that's okay. And then this one would be labeled 2. Well, it's only adjacent to a 1, 4, and a 1. So if I do that swap, so this is what I'm talking about, is I'm going to color U5 5, color that one 5, and I'm going to color V5 blue. So I'm just going to swap those 2 vertices. This is kind of neat, huh? And so that'll be colored 2. And then if I do that, notice that this vertex V4, I wouldn't have to color 4 anymore, right? I could color it 5. And that's what I'll do. I'll color V4 with color 5. So let's see. U4 and U3, I'm going to keep the rest of it the same. Oops. Sorry, I didn't want to. I didn't want to do that. I want to color these the same. So I want to give this a 1. Give this a 1. Give this a 2. Give this a 1. A 3. A 1. A 2. A 3. And that should do it. So I'll just do a quick check, but that argument I made earlier does stand up. I can check this vertex here and the 2 vertices that I switched, and it looks like I can do 4 colors, so that's a proper 4 coloring of G. This is the graph G. I never named it. I'm naming it now. So that's the graph G. And we have a proper 4 coloring. So again, the question is, can we do better? Do you see a way that we could color this with 3 colors? Feel free to pause if you want to keep looking at it. So one thing to notice about vertex colorings, and really what's sort of going on behind the scenes here, how can we relate it to other properties of the graph? Well, the idea is that we're partitioning the vertex set of the graph into color classes. So V sub 1 here is the vertices I color 1, V sub 2 the vertices I color 3, and in general, V sub I are the vertices I color I for some given K coloring. Sorry, I sort of ran out of room there. V through K, that's my, and we refer to these as color classes. This is V1 through V sub K. I'm sorry, this is bothering me. I'm just gonna redo this. Sorry, bear with me, folks. The vertex set of the graph is, right, we're partitioning it up into these color classes. So up through VK. Each of these is a color class, in which no two adjacent edges are colored the same. So that means that if V is in V sub I, or sorry, if U and V are in V sub I, if I have two vertices in one of these color classes, U and V are both vertices, the vertex set of the if U and V are vertices in some V sub I in some color class, then UV can't be an edge of the graph, right? Because if it were an edge, I'd have two adjacent vertices colored the same, and that's not the case with color classes. And so what I'm really doing is what we're seeing here is that each V sub I is an independent set. And so at least here we see some connection to a topic we've run into before, which is vertex independence. So in that problem, the idea was to find a largest set of vertices that was independent. So that would translate here to what the maximum size of what the maximum cardinality of each color class is, right? So the independent set, remember, we let alpha of G is the independence number of G. And this is the most number of vertices in an independent set. Since each V sub I is an independent set as a color class, we have that the cardinality of V sub I is at most the independence number of the graph for each I. We're going to use this later. So everything we know about independence, we can sort of leverage, at least in this way, and see what kind of information we can get about vertex colorings. So a few more definitions here. What were we doing in that last example? We were really trying to find the smallest number of colors we need for a proper coloring. So this is exactly what the chromatic number is. We denote it chi of G. It's the minimum positive integer k for which G is k colorable. And sometimes a graph with chromatic number k we call a k-chromatic graph. So we've seen other properties of graphs that are defined similarly as the minimum of some set, right? The minimum positive integer k or the maximum positive integer k, right? We've seen this in other topics. And remember here, for example, k-connected graphs. So in order to show a graph is k-colorable, we have to demonstrate that we can get a proper k-coloring of it. Sorry, maybe I'm going to write that down. To show G is k-colorable, we need one, a k-coloring, a proper k-coloring. Remember I said sometimes we're just going to say coloring. We mean proper coloring. So we need a k-coloring of the graph to show it's k-colorable. We need a k-coloring of a graph and an argument for why there is no k-1 coloring. That's the idea. Okay, so here we did pretty well, right? Remember, we got this down to four colors. We were able to do this in 4 colors. And let's see, can we do better? So we already have for this graph here, G, we already have a 4 coloring. That was the previous example we did that. So what this gives us then, this is the upper bound. We've done at least as good as 4. And then the question is, can we do any better? That is there a 3 coloring? And so at least we have that the chromatic number is 4. Right, we need an argument for why we can't have a 3 coloring. So suppose we had a 3 coloring. Suppose C is a 3 coloring of G. Actually, I'm going to say something. Yeah, I'm going to say something first before we get into this 3 coloring. So we're going to go for a 3 coloring. I want to say something first, right? Notice that V1, V2, and U1, notice these vertices are all adjacent to each other, right? They form a K3 or a triangle. And so what this means, right, if these are all adjacent to, they each have to be in their own independent set, right? They each have to be in their own color class. None of those 3 can be colored the same. So that's these 3. Can't be colored the same. So actually more than can't be colored the same, but must be colored distinctly. So that is a different color for each of these. I'm just going to say it instead of writing it. These 3 vertices have to be colored distinctly, and so let's say because V1, V2, and V3 are adjacent, mutually adjacent, we must use at least 3 colors. Chi of G is greater than or equal to 3. All right, so we have that it's at least 3. What I want to go for now is 3. So suppose C is a 3 coloring of G. All right, so what we're going to try and do here. So yes, so since those 3 these 3 vertices are colored the same, I have to use, let's just color them right now. 1, 2, and 3. Let's color those vertices now. And then think about, right, so we're restricting ourselves to these 3. And now we'll just try and fill in the rest. So U2 is adjacent to both a 1 and a 3, so we have to color that too. So right, so now parts of the coloring are forced. If I'm restricting myself to just using 3 colors, then these are going to be forced. V3, I have to color 1. And then U3, it's adjacent to a 1 and a 2, so I'd have to color that 3. And we just kind of hope this works out. And if we get to a point where I have a vertex that has to be colored, say, 2 different ways, so that is a contradiction, and we can then conclude that there exists no 3 coloring. So what we're really doing here is, we're assuming to the contrary that there exists one, and if we happen to not get a contradiction, that means we found a K coloring, and then we would have that the chromatic number of G is exactly 3. So this is the idea, and we just keep going through this coloring. And it looks like, so did it work out? No. So I've now come to a contradiction, right? So U5 here, all of these colors were forced, right? As I was going through this, I wasn't making any choices. These were all forced from these 3 being colored differently or distinctly. And we knew that had to have happened. And so that means we would always, no matter what coloring we're given, we would always end up in a case like this if we tried to color it. We would have U5. It's adjacent to a 1. Sorry, I stopped writing numbers somewhere through this. 2, 3, 1. It's adjacent to a 1, a 3, and a 2. And so we can't color U5 anything. So here we need a 4th color. So one way we would do this is we would write this as a contradiction, right? We would say since it's adjacent to a 1 and a 3 here, it must be colored 2. C coloring. Then, so we did a lot of talking here that we would write down. Then C of U5 is equal to 2, but U5 V1 is an edge, and color of V1 is 2 as well. And that's a contradiction. It's not a proper coloring then. So that's the idea of how to argue. So what does this show then? So this shows that the chromatic number of the graph here, so all this information tells me the chromatic number of the graph, which we can say now is 4. There was no coloring with 3 colors, right? So this here established that the chromatic number of G was at least 4. Together with all of this, we have that it's exactly 4. So this is the kind of information that this parameter of the graph contains, and what's necessary to prove. So a couple notes. There's no general formula for the chromatic number of a graph. It's an NP complete problem to determine that a graph is K colorable for any K greater than or equal to 3. And so what exactly are we going to study here if it's one of these hard problems like Hamiltonian graphs? Well, think about what we studied in Hamiltonian graphs. This is a little bit different. So we're concerned with 2 main questions, right, or topics. To determine the chromatic number of some specific graphs, to determine families, right, the chromatic number of families of graphs that are interesting to us, and then 2, to determine upper and lower bounds for the chromatic number of a graph based on other properties of the graph. So this is the idea. All right, I'll end this video here. In the next one, we are going to look at just some basic bounds and chromatic numbers of graphs. I'll see you there.